Well, so far it is a centralized computation. So how can we make this in a distributed protocol? For example, as used in a particular distance vector-based intra-domain routing protocol called RIP, as well as used as part of BGP inter-domain routing protocol and used in the original ARPANET in the 70s. Well, we're going to see the use of message passing. Back in lecture 1 and in the next lecture we'll look at implicit message passing, but today it is explicit message passing. And it can start from a cold start, meaning that nobody has an idea about the existence of any other node other than yourself. Now the good thing about these messages is that A, they are short. How short? There are basically 3 fields here for each message. Node ID, who am I? Destination ID, which destination are we talking about? And cost of the mean cost path. Okay, so maybe is this A, I'm A, I can get to B with 5 units of cost. Okay, that would be one message. And you send this message to your next door neighbors. Okay, those that you have an egress link pointing to. So this is only local interactions of the messages. No need for broadcast to the rest of the world. And finally, at the conclusion of this protocol, each node only has a local view of the topology. For example, at the conclusion of the protocol, I ask a particular node A and say, well, you've successfully completed this Bellman-Ford calculation. Can you please draw me the graph now? And say, well, nope, I do not know the topology, the graph. I only know if there is a packet for node B, I will hop forward this to some of my neighbor, and the minimum cost to get to B is this much. That's it. I have no idea how my neighbor actually will carry through the rest of the job. And I don't need to. That's the beauty of this, that you can even have no one with a low global bird's eye view of the topology, and yet collectively they have accomplished this routing. Now, compared to routing back when we were talking about small worlds in the social network, we want not just a polynomial of the logarithmic of the size of a network, an order kind of result. We want a practically very efficient solution. But the benefit is that we can allow these message passing. Okay, because the message passing is on these kind of cost of mean cost path, it's called the distance vector based intra-domain routing within the same company's network. Now, in the actual routing table that forwarding will be using, you of course have your ID, the destination, and the corresponding mean cost path cost. You also need another information, which is the next hop. Let's say node C. This is one of your neighbors. You're going to have 4 fields in the routing tables, each row. And then when you broadcast the message, however, when you send the message only to your local friends, however, you only need to send the first 3 fields. You don't even need to tell your neighbor how you're going to finish the job. That's your business, is none of their business. They don't need to know how you do your part of the job. They just need to know the cost it takes for you to get to this destination. So the message passes 3 fields. Each row of the routing table is actually consists of 4 fields. So here's a small example. It's even smaller than before. 4 nodes, 5 links, each link's bidirectional. The number next to the links 1, 1, 2, 3, 5 are the link weights. Please do not eyeball the answer. Please do not use a centralized computation. Instead, we'll look at a distributed way to compute Bellman-Ford. You think probably that this is painfully slow and kind of stupid, but just bear in mind that A, computers can do this real fast, and B, in a practical situation, you cannot afford to eyeball the solution or even centrally compute the solution. You have to start with cold start, where each node does not even know the existence of the other nodes. So at time 0, at initialization, the routing table is very simple for each node. Say for node A, the 4 fields are, I'm node A, I can get to A with 0 cost, of course, and the next hop is node A. And that's the only row in the routing table for node A. Similarly, BB0B as the only row in the routing table for node B. So at the conclusion of the 0th iteration, the message you send is just AA0. I'm A, I can get to A with 0 cost. And you will tell that to your neighbors A, B, and C. Similarly, B, C, D will send a similar message to their neighbors. So now at t equals to 1, the first iteration, how can we find out the answers? So let's say not just for destination A, let's say for node A, okay? Let's construct the routing table for node A during the first iteration. Well, for node A to get to node A, I still write down AA08, that's clear. What about node destination B? All right, so for A to get to B, it will be the min of the 3 neighbors numbers going through neighbor B, and for B to get to B, going through neighbor C for B to get to C, and go through neighbor D. So I'm implicitly assuming I'm talking about destination destination B here, okay? You may say, hold on a second, how do I know these numbers? Well, you know the numbers because they just told you, your neighbors. At the conclusion of the last iteration 0, they just send you these kind of messages, okay? So you know the numbers. And you also know the cost to get to these neighbors now, because you have had a way to communicate with them once at this point. So this is the min of 3 plus 0, 1 plus infinity. Infinity because from the message you received from node C, you see, hey, it doesn't even know the existence of node B, so it can't get to B. And 5 plus infinity. So again, you know 3, 1, 5, these 3 numbers because you have had one round of communication. And you know 0, infinity, infinity because you were reading their messages from the last round. And this is obviously 3. That's the answer. Similarly, you can look at how do I get from A to C and how do I get from A to D, and you will see the answers are respectively 1 and 5. Okay. So you can now summarize this as the following. This is the routing table for node A. Okay, I am node A, I can get to A, 0 cost, go through A. I'm node A, I can go to B as the destination. The cost of min cost pass 3, I should hop to B, send the packets to next hop as node B. To get to C, go to C, the cost is 1, and you can keep going down like this. Okay. So this is for A. You can write down the similar routing tables for nodes B, C, and D as well. It's also in the textbook. Okay. Now you can repeat this process. What about iteration 2? You want to write down the routing tables for A, B, C, and D nodes. Here is the answer for routing table for node A. Remember, at the end of the routing round 1, A is going to send the following 4 messages. Same message, AA0. New message, AB3. All right, if you want to get to B, you can go through me, and the cost is 3. If you want to go to C, you can go through me, the cost is 1. You want to go to D, then you can go through me, the cost is 5. So A will send these 3 tuples in each message, 4 messages altogether sent to all its neighbors, which turn out to be B, C, and D. Similarly, B, C, and D send messages like this to their neighbors. Okay. So in particular, now let's look at this entry in the routing table for node A at time 2. It says if I want to, as computation, get from A to B at time 2, that is the min of 3 plus 0, 1 plus what? 1 plus 1. Why? Because from the last round's message, okay, sent to me from node C, I know C can get to node B with a cost of 1. Okay, and then it will be 5 plus 2. Why? Because from the last round of message, I know node D can also get to destination B with a cost of 2. So now I can update these, and the answer is the min between 3, 2, and 7, that is 2. Also, next hop is now C. So instead of 3 and B, those are outdated, replaced by 2 and C in this entry of the routing table. So you can work out the rest to the other 2 entries as well as the rest of the 3 nodes, or in the textbook. And this is what happens after another round. Now, of course, notice we have assumed that there's a synchronized clock. Everybody have the same notion of time and rounds. If that's not the case, I think we have one homework problem talking about what would happen. All right, so you can write down for node A and similarly node B, C, D routing table at the conclusion of round 3. You can keep going, but you realize that the routing table doesn't change anymore. Now, in reality, of course, there are nodes come and go, so it may change all the time. So how do you keep track of both asynchronous behavior of the clocks and also the node's failure? Those are some of the questions practically important and explored a little bit in the homework problem. So finally, we have concluded this long lecture. I don't know which one's longer, this one or lecture 4, but both are very long because we touch upon 2 things here. One is the underlying design principle of the internet. Why has it been so successful? One is packet switching for scalable connectivity and efficiency. 2 is layered protocol stack for efficient modularization. Well, I shouldn't say efficient modularization, I should say for a smart modularization. Okay, sacrificing efficiency of performance for evolvability. And 3rd is distributed hierarchy with the help of overlay network. Okay, packet switching, layer protocol, hierarchy with overlay. We then looked at routing. Routing has many variants and many ingredients. Okay, addressing, routing, and forwarding are the 3 main ingredients. So many different variants. We only got the time so far to talk about a specific case, distance vector routing with destination-based and hop-by-hop forwarding. It's based on the Bellman-Ford algorithm. You can execute it in centralized way or co-start in a distributed way with the help of those message passings. So now this is IP. What about transport layer protocols such as connection-oriented version TCP? We would look at a specific functionality implemented in TCP called congestion control. It is both fun for its optimization methodology, but also very clearly important to maintain the viability of the internet.